Up to now, I tried to explain you basically what SDN and OpenFlow are developed for, but there are other sort of variants that are useful for fully exploit their potential. For example, I mentioned that you could have multiple controllers, even for multiple owners, that run on the same infrastructure. That is a scenario that is also, we will review later in 5G. So the idea is, for example, I have in Trento we have a testbed that is an optical ring, and we would like to make different experiments because maybe I have a project and I need to run some experiments. The research center that is our partner wants to do other. How can we do experiments in such a way that they are isolated? So how can we be sure that my experiment will not interfere with them? It is something that basically natively OpenFlow cannot do it because there is no, the switches are dumb, so the switches don't provide any sort of, let's say, priority, for example, among the requests of different controllers. They just answer. They just answer to the commands. So for this reason, there is another concept that I wanted to discuss with you that is called the flow visor. And it is something that if today we have time, I will show you. Otherwise, you will have the instruction on how to test it yourself. Practically, we need an additional level of abstraction between the switches and the controller, because we would like that if we want different controllers to operate on the same infrastructure, we need an intermediate level which checks that each of the controllers follows the right rules. For example, I can be the owner of the infrastructure, so I want to do everything on my infrastructure. I can control completely the behavior. But maybe a company comes to me and tells me, I would like to make an experiment on your optical network. Can I have, I don't know, 100 megabits per second of a ring just to run something? I'm okay, but I must be sure that if they want to make OpenFlow experiments, so if they want to have their own controller to run that part, I must be sure that they will follow the rules, so they will not interfere with the rest of the bandwidth that I have. And for this reason, one idea that it works currently seems to be a feasible solution is to put a sort of OpenFlow proxy that is called flow visor between the controllers and the infrastructure, so that the flow visor is managed by the owner of the infrastructure, and is the one that will check that each of the controllers follows the rules that are intended for that controller. Okay, so there can be a controller that can control everything, a controller that maybe controls only a few nodes, a controller that only sees half of the bandwidth, and so on and so forth. So flow visor is a level of abstraction that is between the controller and the switches. Okay, it works like this. You have to. The solution that I'm mentioning is on your right. So you have a set of resources. You have the OpenFlow protocol. Instead of having directly the controllers, there are some examples. Open roads, open pipes, and so on. They are extensions of this NOx controller. You put flow visor in the middle so that all the messages that are exchanged between the controller and the infrastructure go under the control of flow visor. Okay, all the messages. This is the same that you have in virtualization. In virtual machines, because usually you have your resources, you have a set of instructions, and then there is your virtualization environment that can assign different resources to different virtual machines. Okay, you can also avoid to have it and just say, okay, each virtual machine will take whatever it wants. But a better way is to have an intermediate layer that controls the amount of resources. If we look in the OpenFlow concept, this becomes something similar to this. Those are the switches, okay? The switches, instead of speaking directly with the controllers, that can be many, you see, they speak with them through the flow visor, okay? And that is the key point for a functionality that we will see in a little bit, that is very well known, and it's one of the major advantages of virtualization, which is slicing. With flow visor, you can implement slicing of the network. So I can slice means I take a subset of my network and show it to one controller. Okay, so one controller will see, for example, these two switches. The other controller will see this one and this one. Okay, but the controllers that share this will have different rules to interact with that switch. So they will not be able to control everything, but only some, for example, specific flows. Okay, that is good because it allows you to achieve slicing. So you can cut your network into several versions. You can cut in bandwidth, you can cut in the topology, and so on. Plus, you can isolate the slices. Okay, the important point why you need flow visor, especially, is that you can isolate. I will show you, hopefully, a demonstration. The point is that you can really isolate the different slices that you build, so that every slice becomes a separate network, and it can have its own controller. Okay, so that is not simply like this, but using this concept, you can achieve, for example, multi-tenancy operation on the same infrastructure based on this concept. I will show you more details later, but the concept is that you need flow visor or something similar, or a proxy, that can help to enforce isolation between the slices. Okay, so there are the two major points of using flow visor is, one, that you can give different abstractions to the higher layer. So you can show different networks to the different controllers, which is already good, but the best is that you can slice and control the exchange of messages in such a way that you guarantee that the networks are isolated. Okay? Here there is some brief explanation. So practically, when you run flow visor, it's not as simple as in the case of OpenFlow, because the network manager should build the slices himself. Okay, there is no, I mean, you can do it automatically if you want with some rules, but in general, there is the intervention of the network operator that builds the slices. Then, by sitting between the controller and the slice, flow visor can do a lot of things. For example, it can check that the controller works only on the flow tables that is intended to control, or on a subset of the flow tables that it can control. And it can also drop messages. So if a controller does something that is not foreseen, that is not allowed, it can be dropped. Okay? So it's easier if I show you this example to understand how it works. So imagine that you have the owner of the infrastructure, then you have Alice and Bob, that are two companies that want to manage different slices of the network. You put flow visor in the middle, so the idea is that, for example, if Bob's controller will issue a command, maybe it wants to pre-configure the switches, then it is intercepted, of course, by flow visor, and then the flow visor will check which are the policies to use in Bob's slice. If those are okay, then the message will be relayed to the switch. The same for the answers. For example, if you see here, message number 4 is a switch that wants to speak with a controller. For example, this switch wants to speak with Alice controller. In the same way, the flow visor controller will check if that is an allowed behavior. For example, because it has to check if that switch belongs to the slice of Alice, for example. Okay, because it could be not the case. In this way, you can isolate the traffic. Okay. Then, of course, again, you will excuse me if sometimes the concepts are very general, but I try to keep them general sometimes because the way you define a slice is up to the owner of the infrastructure. So the slice can be, I have a ring, and all the people will see the ring, but with different bandwidth, for example. This is the slicing, let's say, horizontally. I slice the bandwidth. But I can also decide that in one slice there are 10 switches, in another slice there are 2. Okay? So it's a combination of these parameters. Then, of course, they have to be defined. How the flows belong to the slices depends on the usual set of parameters that you see here. Okay. So because when a new packet, for example, comes in the system, the flow visor has to know in which slice it belongs, because otherwise it cannot send it to any controller. So for this reason, usually you create slices based on the IP address. So you assign to some slices a set of IP addresses, to another one another set, but you might do it in different ways. Okay, that is the simplest approach. You assign when a customer, let's say, of your infrastructure comes, you say, okay, I give you the addresses with 10.00x. Those are in your slice. The other is in another slice. Here they just put 2 addresses in each of the slices, for example. You can do, actually the thing is that it must be a combination of the parameters that can be acquired by the OpenFlow switch. Okay, so you can define the easiest, for example, we did it in practice, and the easiest way from our technicians was to use VLANs. So to say you are assigned a VLAN, the other guy is assigned another VLAN, so when they enter, the switch will know directly which is the slice. Okay, so you can do it. It's very flexible on this. And the last thing that I wanted to show you on FlowVisor is this. This is the advantage and the disadvantage. The advantage is on the left. So here I show you how that you can isolate the flows. Okay, so without FlowVisor, if someone injects a constant bitrate flow, which is UDP, look at the bold ones. So the highest and the lowest. In this case, 2 flows are injected in our system, and one is TCP and one is constant bitrate, so this UDP. You know that when they compete for resources, UDP wins if there is no specific queue management by the router. So you see that the TCP gets almost 0 bandwidth, and UDP gets practically 100%. Okay, this is without FlowVisor, so accepting the flows and mapping. Imagine that there is a bottleneck. They share that. If you include FlowVisor, you can assign one UDP, the UDP flow to one slice, and the TCP flow to another slice, in such a way that the TCP slice is guaranteed to have a given percentage of the bandwidth. For example, here I think it was 70%, let's say. And you see the isolation functionality. So without just enforcing from FlowVisor that one slice has 70 megapixels, the other 30, you see that it's possible to isolate. Of course, not perfectly. There might be oscillations in this case. It's a real trace, so it's not so. But you can see that you can almost precisely slice the network. Here is because TCP, for some reasons, didn't use all the bandwidth, so UDP got temporary advantage. But that is to show you the advantage. So the advantage, you can control better the resources. The disadvantage is on the left, on your right, sorry, and it's this one. So this is cumulative probability to have a specific latency. Okay, so it shows you, for example, without flow visor, so if you're using SDN, this delay that is like this, let's say in average, you get something like, I don't know, 10 milliseconds, is the delay due to the fact that some packets are required to go to the controller. Okay, so the 10 milliseconds are for the controller to receive a new flow and decide what to do. If you include also flow visor, you lose in average, so you must add in average 16 milliseconds because you have an additional level. So now when a new packet is going to be sent to a controller, first of all it will go to flow visor. Flow visor decides whether it's legitimate or not. Then it will forward it to the controller. The controller will send back a message. Flow visor will check again that if that message is legitimate, and then it will forward it. That is the price. So, of course, the price for isolation is small, depending on the setup, but it is an increase in the delay. Okay, because accepting new flows requires further processing. Okay, that is the negative part. So is it clear? So you have, with SDN, you have controllers and the switch. Here you add the proxy in the middle, okay? The proxy is powerful because it is the place where you enforce probably the agreements that you write on the paper with the people that can use the same, that can share the same infrastructure. Of course, Flow visor is an example. It's an actual, a real name of a software, so you can. I will show you. We can use it. Of course, there are other alternatives, but the concept is similar. You must put something in the middle. Okay. Flow visor is the most popular to do this. Just a small parenthesis about the centralization aspect. There is people that went further with the concept of SDN. In such a way to be able to manage bigger networks, okay? Because of course an SDN network is a network where if you put a single controller, you cannot manage so many devices, okay? There is a limit depending on the traffic, on the number of requests per second, and so on. So some people went a step forward and they said, okay, let's generalize the situation. So we will have a large network, so let's say an infinite number of devices, and we want to manage this infrastructure in a software-defined manner. So we want to have something similar to the controller concept, but more scalable, okay? What they came out is the idea of the Open Network Operating System, or ONOS. So the idea is that it's logically centralized, but it's physically distributed. And I will show you, just, I don't go too much into details, but I'll show you the architecture. So the idea is that those are controllers. So the idea is that you have several controllers. In this case, the problem is not sharing, but coordinating the controllers. So what they put is they put another let's say bigger level of abstraction that interconnects to all the controllers in such a way to have a global vision of the network. Okay? And then of course you need some distributed registry and event notification that are properly managed. On top of that you have the application. So practically the idea that they have here is that they add a new level that is able to help the controllers to coordinate, okay, practically speaking. And the only way that you can do it, you cannot go below, because the controller should be near to the infrastructure, as we said. Maybe we can put the flow visor if we want to share, but that is not necessarily the case all the time. What they do is that they put something on top that can coordinate the controller. So it is like having another application layer below the application layer. So here you have the logic to manage a piece of the infrastructure. The highest level collects the information and coordinates like an application does. So it issues commands to the controllers to coordinate the different subnetworks, okay? It's not a big revolution, it's just to show you how you can generalize the idea to have multiple controllers and how to coordinate them, okay? If you are interested, there is, I think I didn't put the link, but if you look for ONOS, you can find it easily if you are interested in the details. It's not, let's say, with respect to the difference that you have between traditional and SDN networks, this is just a step forward, okay? And right now they are working in defining what to put exactly inside those parts. For us it's not much important because it's, in the cases that we will see, we can even assume that there is a single controller, okay? It's not necessary to have all this stuff. But in general, one of the questions could be, what do you do if you have maybe millions of devices, okay? A controller cannot manage so many, so you need something like this, okay? Again, it exploits the fact that you don't change OpenFlow will be here. What you build something on top of the northbound interface, so you are free to put whatever you want, okay, on top. It doesn't change our concept. But let me instead move to another concept that usually is sort of mixed up with SDN. The thing is, software-defined networking and network function virtualization go well together, okay? In fact, today we will finish merging them, but they are not the same thing, okay? There is a lot of, say, errors in defining those things. So SDN is what I discussed until now, which is practically detaching the control plane from the data plane, centralizing it to enable the network to be programmable. Network function virtualization instead is another concept, and it has a bigger impact from the architecture point of view, because the idea is that in this case you use virtualization technologies to virtualize network node functions. So the idea is that you take the functionalities, some functionalities of the network, maybe all or a subset, and you make them building blocks that you isolate in practically in sort of virtual machine or containers, and then you will rebuild your services combining these blocks. Okay? Someone will say, okay, which is the advantage? The service is the same. Yes, the difference is that being virtualized, you can move these functionalities, you can allocate more power, for example, to some functionalities. You are more free to move them around, duplicate, turn it on or off. That is a way to provide more flexibility to the system. And it will be a key point, this one, for 5G. Because some functionalities are required to be activated only when needed. You don't need them all the time. But maybe there are times in which you need more power, let's say, or more capacity in a point. If the capacity is processing, you need to have an approach like this, where you can activate the software or move your functionality where you want. That is the concept. Then, of course, it comes with a lot of complication, because today we have this situation. So I want a firewall, let's say a commercial firewall. I will need to buy hardware and software, this kind of some device like this or a rack component. I'll put it, it's a firewall, very well. I position in the most strategic position, and I'm fine with that. But then maybe I want to do deep packet inspection, and then it's another thing in my rack. Then I want to for example, use some wide area network acceleration techniques, or that will be something that we will discuss later on. I want a radio access node to deploy a radio access node. Of course, I can do it, today I can do everything very well and very reliably. I buy the hardware, I install it, and I run it, okay? So, already a disadvantage is that it requires time. Because if today I decide I want to do deep packet inspection and I don't have my device, you can trust me that in Italy the bureaucracy is so huge, let's say, that it will take 3 months probably for me if I have the money to get that equipment running in my lab. Maybe you are lucky and you can buy one in some weeks, but still it takes a while. You know, if you want to change or increase the performance of your network, you need several days at least to deploy them. The approach with network function virtualization is that you will have virtual appliances that implement the functionalities that you have on the left. So instead of having a firewall, you will have a virtual firewall appliance, which is a software that you download and you install on, for example, you have a rack of servers, you have a server farm or even common PC, depending on what I want to do. I install it there and it runs visible in seconds, maybe minutes. I have my firewall running. Of course, the complexity is not much to build a virtual machine or a container for my application, because that I can do easily today. Okay, I build it and I ship it as a software. The problem becomes that I have to rebuild the flow that my packets do in the real hardware. So for example, I want my packet to go through a firewall, then through deep packet inspection, then through whatever other component I want, and so on. I need an environment that, regardless of where I put my appliance, through orchestration, it can build, let's say, a path for my packets so that they get exactly the same kind of service. Okay, because the thing is, if I virtualize the things, they become sort of abstract. So I have the complexity is that I must have a language also to describe what is the processing chain of the packets, for example, or how the flows should go between the firewall, the router, and so on. So this comes with the price that before it was a physical situation. So you plug the output of one block to the input of the other. That is the physical link, the packets will flow that way. Here instead, the manager wants the freedom to move also the appliances where it wants. So the system must follow the position also, okay? And allocate proper resources and networking. That is where SDN also comes in the picture, because this works well if your network is easily reconfigurable, because maybe the path that my packets do can be dynamically reprogrammed in such a way that my packets will go in the right server directly, okay? So that is the boundary between the two, if you want. Just to be a little bit more clear, here there is, it's not actually NFV against SDN, but just a comparison to be more clear. So they have similar goals because the idea is always virtualization to some extent, more flexibility, but they are different because SDN provides new interfaces and as I was telling you, detaches the control part to make the network more flexible. With NFV, the idea is that we detach network functionalities or services also, and we want them to work wherever we want. Okay, here they say on commercial, this I took from a NetC document, they say on commercial off-the-shelf hardware, to say that in principle a service would run everywhere. Okay, of course, depending on where it runs, it can have different performance, but in principle, the container should be independent from the hardware. Okay, So if you want, SDN detaches the control part from the hardware, NFV detaches the service from the hardware, okay? Then, as I mentioned you, it's very good to have this. That was the famous paper that I mentioned before. So several years ago, in 2008, actually it was not, the main idea came from my PhD student at that time, which was Dimitri. We started to propose this idea because we were calling it distributed protocol stacks, but the idea was to itemize some functionalities and move them around, because in some way, some situations, some functionalities of the protocol stack are most useful in another position. Okay? I don't go into detail because we are already delayed. There are some slides if you are interested to check. But our problem was that at the moment there was no standard interface for doing this. So the weak point of our proposal was that we would need to generate an ad hoc protocol for detaching this functionality, okay? It was a weak point because this would have required to change the access point and the mobile system. This is in a wireless sense. So it was not feasible at the time. Today, in principle, if we will have NFV, that is exactly what is being implemented, okay? Here is the concept. So the idea was that, for reasons that maybe they are not familiar to you, but since the wireless part, if the end part is the wireless part, it has a lot of problems about the reliability of the channel. So some functionalities that are from the transport layer could be moved directly to the access point to make things faster, okay? The problem is that, in fact, here you can see we were proposing to put a new protocol, mobile interconnection protocol, that is the name that came out, because there was no framework. Today with NFV, luckily, okay, here there are some other examples, but you can check the paper. I don't want to waste time on this. Today, instead, the idea is that if the network function virtualization would be deployed, that would be natural. So it would be required to have a specific protocol, because the architecture that I will show you now will be able to offer the functionality that we were missing at the time. Okay, not to show that we embedded something to change the world, but to show you that sometimes there are works in the literature that come at the wrong time. You get in a time where you don't have the structure to make it real, while sometimes the idea is good. So in this example, this is what you need to make NFV real. So you need a lot. Of course, you need to have to identify network functions that you want to abstract. Can be anything between say protocol functionalities to services. Okay, I was mentioning before a firewall can be deep packet inspection functionalities, security, authentication. There is a full list later on, so I will show you that everything can be virtual. Then, of course, you transform the network function in a virtualized network function, which is when your system builds the standard container for your service. But you need other things. You need a VNF forwarding graph. So you need to define how the system will process packets. So the order, okay? It's called forwarding graph. For example, could be firewall to the net, to the load balancer, or any other order that you think is useful for you, because you need to say how these services or these virtual functions are interconnected. Then you need the network virtualization, network function virtualization infrastructure. The infrastructure is the environment where you can run the virtual functions. But not only this, this is available, okay? You can use OpenStack, you can use other solutions. What is the key point is the last one. You need a framework for managing the whole system. So you need network function virtualization management and orchestration functionalities, because you need to manage the virtual function. So you need to have some process that can monitor your functions. Maybe they freeze, they die, you want to change them, you want to monitor if they are overloaded or not. So you need this, but you need the orchestration because you need to allocate the right resources. Can be computation, can be networking, can be storage, or a combination, to each of the virtual functions. That is the key point. It's not, this is the difference between running, as I will use today, between running a virtual machine in VirtualBox, best effort, so say, okay, I hope that my machine will support the process that I need, or having, let's say, carrier grade or QoS enabled system. Okay, for example, the firewall will need an amount of storage and a connectivity of a given level. I cannot say, okay, I give this firewall whatever it gets from the system. Okay, so you need the orchestration because this device is monitoring, like in a data center. You know, in a data center you have an hypervisor, it's called hypervisor, or there's other names that controls how the virtual machines operate, where they are, whether they should be moved, whether they should be duplicated, whether the content must be moved in another position. That is exactly this, and it's very complex. Okay, it's called usually the acronym for this is MANO, M-A-N-O. Okay, if you look MANO, you see thousands of papers because now it's the hot subject is how you manage that part. Okay, I will show an example, of course. But that is the most complex part because it's how you map the virtual world. Okay, up to here, everything is virtual. So there are pieces of software in general. I mean, I'm exaggerating, but there are pieces of software somewhere, randomly run somewhere. If you have this, you have full control on your system. So you know where exactly the functionality is at the moment, how it is going. You can connect them, you can remove them, or duplicate or allocate more resources dynamically. For example, a typical problem that can arise in a cellular network is that you have a hotspot of traffic that must be managed by one of the base stations because it happens that the people gather in a position. Okay. So usually you run scarce of resources because each base station will have its own set of frequencies, its own bandwidth, and also of power, of processing power, because this base station can manage up to a given number of connections. It cannot go beyond. So the only solution usually is you reject some connections, hoping that another base station will be able to take the load. In this approach, instead, if your network is really flexible, okay, I'm telling you, in the ideal world, you could face the same problem, but ask the network to allocate more resources and more processing power, for example, so that the base station becomes, let's say, bigger, more powerful. Then when the users go away, you can say, okay, I redistribute the power that I had to other. Okay, so the idea is that that is done flexibly to be competitive. Okay, if it's like a fixed allocation, you can do it today. You take it's similar to managing a data center. Okay? A lot of companies are doing it very well today, so it doesn't change much. The idea is to do it based on the context of operation. Okay. Let me. This is practically an idea of how you merge the network functionality. So you can have here. You cannot read very well, but it's network as a service. So by SDN, your network becomes a service also. Then if you include also the hypervisor, the processing part and so on, you get the infrastructure as a service. So you have a full infrastructure, networking, storage, and processing. And on top of this, you can implement, in general, virtual machines if you want, okay? However, there is a problem with virtual machines, that they are slow. Here is, let's say, a very approximate discussion, but just to tell you why today there is a very wide variety of containers. Probably tomorrow some of my colleagues will tell you more about this. I just left you some slides for information. This is an example of what happens if I deploy, if I want to deploy a new service, let's say I need a firewall, in different solutions. The bare metal solution is I buy the hardware and software firewall. So it will take days, probably, hours to be configured and connected, and then, okay, it will boot in some minutes and be operating. One other solution is I take, for example, a Linux virtual machine and use it as a firewall, okay? So this is the middle line. So I can download a software, like I asked you to do for this afternoon, to take minutes, hopefully. Of course, some minutes to configure your machine, and then in seconds you run it, which is much better, okay? Of course, the other version, maybe it will be better, but to some extent, maybe you don't need all the complexity of the dedicated machine for doing the firewall. Today, the idea of network function virtualization is to go towards lightweight virtualization, which means that you don't virtualize the whole virtual machine. Okay, today what we do in our laptops or our desktops, I use Mac, so unfortunately some softwares require Linux or Windows sometimes, so I have some virtual machines to run those stuff. However, the problem in that case is that I'm virtualizing the full operating system, which is why it takes a long time also to download it, because if I want a new machine, it will be some gigabyte, maybe hundreds of megabytes, if I'm lucky. But for some functions, for example, a firewall, you need a very basic slice of your operating system. You just need the basic networking functionalities, and then the app, let's say the software that implements the firewall. So in this version, the idea is that the download, so the size of your virtual machine will be much smaller, okay? There are examples of basic implementations that are some tens of megabytes, okay? So there are some apps that today you can download in seconds and run it in seconds. So this will enable to exploit the flexibility of the environment, because in seconds you can move them, okay? Think also that if you move, for example, I was running a Windows virtual machine with quite a big amount of software. It's very easy that your virtual machine will become 50 gigabytes. Okay, if I want to move it around, of course I can have optical fiber, so, but it still requires time. If my machine is only the software that I need, probably in seconds I can move it in another place. I can duplicate easily. Okay, so that is why instead of speaking of virtual machines, today they speak of containers. That is this solution. The containers tend to have a very basic, let's say, implementation of the operating system, and they resort to some functionalities of the host system, okay? So they simplify the weight of the virtual machine. So you don't have one machine inside another machine. You have a slice, let's say, since today we're speaking about slicing, a slice of a virtual machine inside a complete machine, which makes it faster. Okay, if you're not familiar with this, I left you some, okay, here there is the advantages, but I think I already told you. If you are interested, I put two slides with some examples. Today is very popular, this one, Docker. It's very easy to use. I mean, I suggest if you are interested, you just Google Docker. By the way, Google is using Docker in its data centers. And they have different versions. It's mentioned somewhere. They have an optimized version because they have a public version and an enterprise version that is a little bit more heavy. But it's very nice, this one, because in Docker, you can just, it's a command line command. You can say, okay, I want to download, there is a marketplace, You say, I want, I don't know, a NAT. I want a device that makes network address translation. If you know the name of the software that you want, it will probably be, I don't know, 50 megabytes. It gets down, you can activate it, monitor it, and do a lot of things. It runs on every platform, from Windows to Linux, Mac. I have it also there, but I don't have anything really running right now. It's very simple, which is an evolution of Linux containers. If you like Linux, that is very popularly used. Or there are other solutions. Even Windows, they have some. They have this sandboxy, okay, which I think that's what they use for backward compatibility or things like this. But there are several solutions, as you can see. The choice here depends on the level of complexity and, for example, the security, because there are solutions like BSD jail where it's practically your container is isolated. I mean, you use fully the Linux, it's only Linux, that one. So you use fully your Linux kernel, okay? Then what you do is you have a separate directory and you cannot exit from that directory with your software, so that you are isolated there and you install your container there. So practically, it's not truly virtualization in the sense that I was telling you before, but it's a trick to be hosted in an operating system without being able to impact on the hosting platform, okay? Still, it belongs to the container, but it's very lightweight, okay? Because practically you are just installing an app, okay? Yes?
We talked about moving service. I had a question there.
Yes.
Normally, network services generally have lots of TCP connections with each other.
Yeah.
TCP, SCTP. What happens if you move it somewhere else? Because if, let's say, if you have TCP, SCTP, whatever, a string-based connection,
Yeah.
you move it, and if you lose just one package, it will be broken. It will broken, and the service will delay for
Yeah.
some moment.
That is in fact.
It should carry IPs also. It should carry all packages, or it should forward them, right?
Yeah, it is basically for services that you cannot, because there are two ways to move the software. One is you close and open again, so that is not your case. So that is the simplest way. I just move the functionality and reconnect everything. If you want to do that, which is called like hot swap or things like that, so you, yeah, like a handover. In principle, you can do it if the network also helps you to manage this mobility, because then the network can, even if you maintain the same IP address, if it's software defined, could actually mimic the fact that you are in the same position but changing the route. Okay. Of course, you need. That is where the orchestration comes in the picture. You need an orchestration environment that enables to have this. So probably it will use some IP assignment that allows you to maintain it even if you are moved within the environment. Of course, you cannot go outside of that. But there are some ways to do. Of course, let's say the live migration is still let's say under heavy development, because it's feasible, but of course to have a seamless migration, so without losing packets, it's an issue. Okay? In principle, it is feasible if you don't go too much far away. Okay? And if you prepare the system, because for example, router migration is another thing that comes out. So you can migrate a router because maybe you want to relocate it for some reason. In that case, that is a live migration. Some people are proposing to have a very short, let's say, not downtime, but freezing time that doesn't impact on TCP, because you still have a small, let's say, amount. If it's an emergency migration, router migration is an emergency situation, like your machine is crashing, or so you have to find another place. In that case, what they proposed is to find a way to freeze the state and to have another machine that is exactly the same, where you just rewrite the state. Okay, but of course it comes with a lot of rerouting. And in principle, it is possible. I mean, not not if you are using Dockers. You must have the full. Now I will show you. Must have the full environment running. Okay, which today is not yet completely, let's say, robust. I will show it's a combination of several software, so still that will be not so easy, but it is in principle feasible. Okay, I will arrive it in a minute. This is for what happens with virtualization. So practically, you put it in a box. You have these circles represents input/output. So you connect. It can be with a single component. You can have a virtual network function that is much more complex, okay, depending on what you do. It's the same. Here are the examples, and then I will show you the architecture that is quite interesting. You can virtualize everything, okay? Security functions, policy control, this we will discuss later, hopefully if I have enough time. Home routers, CDN, so content delivery networks functionalities, elements for doing tunneling, deep packet inspection, QoE, signaling. In principle, everything that you do, it's a piece of software. So practically, you could think to become a virtual network function. I'm not saying that everything must be virtualized. Okay, there is the potential to do this. How you do it? This is a slide I stole from Open Network Function Virtualization Consortium. It's quite complex. So the whole structure is like this. This is the network function virtualization infrastructure. So this is where you virtualize your hardware devices, computing, storage, and network. Okay. Of course, SDN is here. So it's a functionality that is offered there. So you have virtual computing resources, virtual storage resources, and virtual network resources. That is the usual level of abstraction, because you must have a level to manage then the mapping between these two. You have the virtualized infrastructure manager, that is the one that controls this part, which speaks with the orchestrator, okay? The famous orchestrator is there. So the orchestrator must, this is the environment where you have the virtual network function with their own management part. The orchestrator speaks with the virtual infrastructure manager and the manager of the virtual network functions, so that it controls the sequence, so the chain, and that doesn't control, but it gives information about how to map the virtual network function to the virtual resources that are then, by the virtual infrastructure manager, mapped in the real resources. Okay, so that is basically the overall structure. And to obtain this, there are softwares already. For example, this part is the famous OpenStack software environment. So this is what enables to have the virtual infrastructure manager, because it's the OpenStack is a way that allows you to manage a virtual set of resources, so that it's the key for managing the whole infrastructure. Then, of course, this is a famous controller. It's open. OpenDaylight is a famous OpenFlow controller. This is an implementation of an OpenFlow switch. We are using it in Mininet today. Then, of course, depending for virtualization, you can have, mostly it's Linux technology, but KVM, libvirt, or other Linux functionalities. So they all come together, okay, in this system. So it becomes quite a complex system. So imagine, practically, you have, let's say, a set of resources that are in your lab, let's say. They are controlled by this environment. This is also where the virtual network functions are implemented. So the virtual network functions will be implemented through the functionalities of this environment. this is one example. Of course, Open Network Function Virtualization Consortium focuses on open technologies, okay, so they are the ones that are mentioned here, but you can have different ways to do it, okay? I don't want to enter too much into the complexity because it's very, if you're interested, Etsy should come out with a standard, I think next year, in March, I think, with this management and orchestration, so the Mano, it's the famous Etsy NFV Mano, that will standardize how the whole system should work. And you see, it's it's fairly complex, okay? And another way to look here is an example to show you how the orchestrator is a very complex object because it gets in input. That is the VNF forwarding graph. So this is the famous sequence of operations that are chained together. Then, for example, depending on what I need, I can have virtual network function description. So here is where I tell which network function from the catalog I want to deploy, but also virtual network function link descriptor. So how I would like the links to behave, because I can say, okay, between the firewall and the load balancer, I need 1 gigabit per second, okay? So the network should provide me this. And also, sometimes I need physical network functions, which means, I don't know if you can read it, but there is, you can specify the reliability of the link, which kind of links you want, the features, and so on. The orchestrator gets in input everything, okay? And then it controls this part, which is, it has some records to monitor the virtual network functions, as well as the service chain. So it will define how to map the things, and then it will ask for the resources to map those virtual functionalities. Okay, so it's even though network function virtualization seems to be simple because we have virtual machines, to fully deploy these functionalities is still something that it's not today. Okay, we can do something today. If you are interested, if you use OpenStack or similar environments, you can do a lot of these functionalities, but to fully exploit these advantages, we will need proper orchestrators and optimize the behavior of these kind of systems, but that are very, very complicated, okay? Much more than maybe SDN per se. Another thing, so let's put them together just to show you an example of slicing, okay? So what I mean by slicing, especially using SDN, FlowVisor and similar, you can achieve slicing of your infrastructure. You can slice bandwidth, you can slice the topology. Of course, you will slice the traffic because usually different flows will belong to different slices, unless you are doing some multicast or something like this. But you can also slice the device CPU. If you have the whole network function virtualization environment, you can also control the amount of CPU. You can slice the forwarding table, so you can keep, for different controllers, different forwarding tables. Like I was telling before, this is an example that we did last year. This is the real network that we have. It's a ring, optical ring, with 3 OpenFlow switches in 3 different locations. What we wanted to demonstrate here is that by using the FlowVisor that is there, we can allow controllers that connect remotely, okay, they can be everywhere in the world, to control a slice of the infrastructure. For us, the slice of the infrastructure is a slice of the bandwidth plus a virtual machine in each of the nodes, okay? So the idea is that if someone wants to make a test in our network, it will require some bandwidth, and depending on it, maybe it will pay or not, let's say, because we have also other experiments running. And also, it will have the possibility to deploy the services in some virtual machine. Otherwise, it's very difficult to test something, let's say, service-based. So what we did is practically something that I will show you also in the afternoon. We demonstrated that by Flowvisor, by defining these three slices, of course, you have to tell the Flowvisor which will be the IP of the controller, because it has to know where the request will come from. There we sliced very simply, because there were other experiments. We decided to slice 1 megabit in the first case, 10 and 50. And then we made tests. This is a simple ping to show that there is isolation, so you cannot ping machines that don't belong to your slice. And then also here there is a small capture. We made a bandwidth slicing test. For example, this is the first slice. You can see that the throughput of TCP was almost 1 megabit per second. So it was, we could isolate it from the rest of the network. So that is just to show you, it took us not much time, okay? In a couple of weeks, you can configure the system and run it in this manner. And that is what I will try to show you today when we do the practical part, okay, how to do similar things. And we see that it's relatively easy. Of course, there is a little bit of programming, but it's quite straightforward. Before the break, actually, because I think we have 20 minutes, the other part of the presentation, which it will be between now and the beginning of the session at 3, is how these things come in the picture of 5G, okay? Because I was mentioning this is a hot topic, so why should we bother about SDN or NFV in 5G? I save you, I mean, if you're interested, you can get sleepy with this. You know, everyone knows what's happening. You know, the boom of traffic data, which is continuous. The fact that to comply with the required increase in capacity, probably densification will be one of the key issues in 5G. So you must have smaller cells with high capacity. And for this, special use, interference, and also investments become a key point, because to cover a big territory with high throughput devices will become a challenge. For this reason, our idea is this one. So if you like, there was a paper, I think a couple of years ago, where of course, we took the big picture to say that today we can virtualize everything. So let's virtualize also the access network and the cellular network in such a way that in the future everything will be virtualized. Okay, so depending, and here the key point is to see these three colors. Depending on for example, depending on the type of service, you need a different model for your mobile network. Because, for example, one of the applications of 5G is very high throughput, of course, high peak throughput, gigabits per second to the user. And that is, let's say, it can be done with an evolution of the current architecture, because you need more capacity, more wireless bandwidth, practically, which is something that can be done. But if you want, for example, low latency applications, like I want to control a robot or for vehicle communication for safety situations, you need a very, very small latency that today is not guaranteed by LTE or LTE Advanced, because you need a different architecture to do this. You know, you had yesterday also the idea of fog computing. We will get back to it. The thing is that how can the mobile network at the same time give you high throughput, very low bandwidth, very low deployment time, let's say, be able to interconnect in the same way myself with gigabit per second, or a sensor that generates maybe 10 bytes per hour, okay? There are different things, and they don't comply with the same model or architecture for deployment. So one of the possibilities, I'm saying that it's only one. We don't know if it will be the right one in the future, even though apparently 3GPP is going in this direction, is to have a more flexible infrastructure, which is a virtualized version of the mobile cellular network that exploits the concept of network function virtualization and software-defined networking to become more flexible. And for example, to provide one slice, this is why I was mentioning these colors, to appear different depending on the application, okay? For example, if I want high throughput, which probably will be the first version of 3G, of 5G that we'll see on the market, it will be high throughput version of LTE, practically. That can be done with the current infrastructure, maybe with more cells, but not much, a revolution. We apply, of course, the best of the technology for massive MIMO, to beamforming and other things. This is something that can be deployed relatively fast. But then, if you want to use the same network for IoT, for example, it's not appropriate. Because IoT, yesterday you got a very big, very nice also overview of the differences that it's not the same. An IoT device is not a smartphone. It's very different. It generates different traffic patterns. The problems are different. So the network should adapt to that. One way to adapt it is through virtualization. So to have a slice of the network that is isolated also, maybe from the users, let's say, slice, that is capable of providing maybe low bandwidth, but interconnect billions of devices, okay? The same for vehicles. If you want very low latency, probably you need a different slice with different functionalities because you need different features, okay? So that is why the second part will try to provide you an idea of a possible roadmap, because it's connected to how the standard is evolving, on how virtualization will fit in 5G. As I told you, there is more material than what I survey. So there is a couple of examples here, but I cannot get into details, of another practical example that we did, slicing also the Wi-Fi. So you can also slice Wi-Fi if you want, and guarantee bandwidth, okay? But it takes too much time to explain. If you're interested later on, I can come back. Since not all of you are familiar maybe with LTE, some of you are already, I put this slide as for your information. It's told directly by Wikimedia, so you can, if you are not, let's say, if you don't know the details, you can go there. They explain you all the acronyms that you have here. But basically, what we have today in LTE is we have the radio access part, which is practically the user equipment. This is the user. The node B, which is the base station. And then you go in the evolved packet core, where you need different nodes. This is for mobility management. You need to have gateways for services and for interacting with the internet, for example, here. And then you have these two items which are for accounting, billing, service control, if you want, and also maintaining the services that the user is subscribed to. Okay, so this is a database where there are the users, and it is used also for mobility. This is where you have accounting and you are granted access. In the diagram there is also written a possibility to use the same packet core including Wi-Fi small cells, okay? This is not required, but the standard allows to have this functionality. So that is basically, the system is like this. So usually those are real nodes in your network, okay? So what we virtualize can be functionalities. Of course, you can even virtualize the user equipment, but let's not go too much in the science fiction. The functionalities that you need are basically, that is the interface where you start to be wireless between node B and the user equipment. This is for mobility. so to manage the location of the user and the connectivity, and then you have a management part, okay, basically. And then the others are routers, practically. So this is what we have today, okay? We have mostly this situation. Let me go in the second set of the slides to start, then I will stop in 10 minutes, so to be quite fast. I will try at least to show you the why you need the flexibility. This is well known, I will skip it, so you know there's a big increase in the traffic, and this means several billions of users and so on. So it's not, the thing is that traffic on the mobile is exploding much faster than on the wired part. So the mobile networks go very easily in problems of bandwidth availability. Another problem that comes, that is, in my opinion, one of the two best reasons for having more flexibility. It's quite impressive because that is a diagram that I got from one of my colleagues that works for a company. If you look at the revenue of a typical operator, it gets 50% of the revenue from 10% of the sites. So if you are a mobile operator, you should expect that even if you deploy a big network, most of your income, half, will come from 10% of what you put in the field. Because of course, there are hotspots, of course, some places you cover the area, but maybe with very few customers, and also because the coverage is practically fixed. Once you position your base station, you have some, let's say, day-to-day ways to control, maybe a little bit the power, maybe reallocate locally the frequencies, but in LTE you are using only one, so practically you have very limited control. And that is why the fixed architecture doesn't work today, because even if you go to 80% of your revenue, you only require 30% of your sites, okay? On the other side, the guy that is the only one customer in that base station that doesn't provide you any revenue wants that base station because it wants to be connected. So you cannot say, okay, I will just deploy 10% of my network, the other I take back because so that I gain more. But I don't have any other possibility because it's a matter of resource allocation. In some places I waste the resources because I have bandwidth, but I don't have customers. In other situations, I have too many customers and not enough bandwidth. And what the best that I can do is to increase adding small cells, for example, or adding base stations in the areas which are more profitable. So I know that the people will go in the center of Milan, for example, in Italy. So there is a very high density of base stations to try to capitalize on the fact that some areas are very profitable. But still you will lose a lot in other areas because the network is not much flexible, okay? The other thing is that because of this, because you need to increase continuously the capacity of your network to support higher bit rate, more users, you go in the other situation where you have the end of trophy. Okay, here is actually for Asia Pacific, but in every place will happen this trend. There is a time, or will be a time, here there was, because it was 2014, where there is a crossing between the revenues per gigabyte and the cost per gigabyte of the operator. So there are, in some situations, the amount of money that you put in the infrastructure is so much, even because just to power up a base station is a big deal in terms of energy, so it's electrical bill, so you pay directly, where there is no way to recover. So here, you go in a situation where the price for gigabyte the revenue that you can get is smaller than your investment. Okay? Again, this happens because users are varying, they are moving around, but they still require very high capacity when they are connected. So it might happen that your infrastructure is too expensive. Okay? So this is, my opinion, one good reason for having more flexibility. Another reason will come in a minute, but let me just show you, for this reason, already in some places, for example in Sweden, from what I got from my colleagues, some years ago it was mandatory, it was a rule from the government to share the infrastructure by the providers, and they increased a lot their revenues actually. You can share your infrastructure, so of course I'm not telling you how to do it, or whether it's possible today or not. Today is the standard allows what is called site or passive sharing, so just to share the physical location and maybe the structure that you use for the antenna. But we can go beyond. If you would go beyond to be able to share the radio access network, the backhaul, or even the core network, they expect those are quite a relevant percentage of advantage economically, because of course sharing is better. Okay, you share the cost for deploying, or at least the company that deploys can get back more money, okay, by disagreements. The point is, usually you can extend easily the coverage, because maybe one mobile company is on one side, another mobile company is better in another region. If they share, they both get a higher coverage, so they have more customers potentially and they gain more. Sometimes you want to increase capacity in some hotspots. The easiest way, of course, is through, let's say, roaming through another operator, and so on. So that is not actually the key point for virtualization. But of course, I can tell you that today is very complicated, for example, to share the radio frequency part. Instead, it will be something that I will show you. It's much easier with virtualization. But the best, in my opinion, the best situation is if you look here, or maybe later, but yeah, this is a nice diagram that shows you the difference between 4G and 5G. 4G is the dark, 5G is the biggest picture, to show you that you have to improve everywhere in terms of density of devices per square kilometer, energy efficiency, service deployment time, reliability, latency, mobile data volume, peak rate, and mobility. Mobility, let's say, it was fairly good, but the other things are impressive if they would make all of them in the first release. What is more interesting is this. There is a document by 3GPP about the scenarios, okay? They're called business requirements, but practically they are the scenarios. You cannot read very well here, but I will comment for you. These 5 arrows are not positioned randomly to the outside, but I find them very significant because they start from the center point, which is what we have today. They all go in opposite direction, and those are the scenarios where 5G should operate. They go orthogonally. For example, this is enhanced broadband, okay, which is, of course, probably the first release that we see of 5G will go probably in this direction, so it will give you maybe gigabit per second, okay? We don't know, but let's assume. It is in the air. I mean, if you have more bandwidth, more efficient coding, better, the biggest number of antennas, for sure you will get more throughput. Okay, that will come. I'm not saying that it's simple, but it is reasonable that will happen. But there are other things. For example, vehicle 2x. It goes in the opposite direction. Why? Because here, for vehicle communication, a lot of the communication is broadcasting, so you need to have local broadcasting of information, and also you need very low latency. Because, for example, if you use vehicle communication for automatic braking, you have, let's say, probably 50 milliseconds at maximum. Even if you have a robot that brakes, to to stop your car, because then of course the car will move in the meantime. So here you have a mixture of multicasting, let's say, and low latency. Massive machine type communication. You will have massive devices, billions maybe, low throughput, okay, in general, relatively low throughput. Then you have critical communications. Critical communications, you must have very high reliability, which is, in some sense, for a telecommunication person, a sort of orthogonal. Usually, when you build a new system, you say, okay, the throughput is higher. I'm happy because I improved the service. Latency is smaller. That's fine. Reliability is higher. Usually, of course, it's something practical. So the real engineers that deploy services must certify that. But usually, we don't design the system because of that reason. While, for example, if you use 5G for smart grid, for some applications, you must have 5 nines, 99.999% of reliability. It must be certified. The power engineer, yesterday my colleague was saying, if you speak with a power engineer, they don't care about throughput. I mean, of course, they must get what they want, but they don't care about peak throughput. They will tell you the message must arrive there in 10 milliseconds. Otherwise, your system is a crap, okay? I don't accept anything that doesn't go this way. So this will have another set of constraints, okay? So in short, just to close for the lunch, this is, in my opinion, the best way to tell you that there is a problem in 5G, there will be a problem. You need an infrastructure that is so efficient that it can adapt to all those services, okay? You don't want, of course, to build 5 networks. 5 networks is a stupid thing, because if we are already in a point where the revenue is smaller than the cost, if we do 5 times, I don't know how we can do it. Maybe for some application we might, but the thing is, if this must be 5G, and if 5G must have a single architecture, you must have a very flexible architecture, okay? So I'm not telling you that you need to have SDN or virtualization, but what I will show you in the afternoon is that you might think to solve this problem using virtualization, okay? In the current version of the standards, if we stop the time today, they practically are addressing this. So the first release, the last releases, or the ones that are coming now, they focus on increasing the throughput, maybe reducing the latency, but not guaranteeing much. So they focus, of course, at the beginning to increase the capacity of the network, because that is for sure, I mean, doesn't hurt the other ones. So right now they are focusing on that, and they almost completed the standard. So that will be OFDMA and so on. So it's similar to LTE, massive MIME, whatever you want, but those kind of things that were already in the air. Now the standardization is moving to support the other services. Okay, so now they are addressing, and it seems the one that I will show you, they come from some research group in standards. They are checking if virtualization can be one of the ways to increase, for example, to enable infrastructure sharing, to enable adaptation of the services and so on. So that is what I will try to explain you briefly in the afternoon. Then I will leave some time for the practical part. Okay, so that will be, in short, what we will see after the lunch. I think we already delayed, so the only thing is if there are any questions, maybe even later offline when you want. By the way, if you have any curiosity also, feel free to drop me an email even later on. Okay? I'm very happy to answer, if I can, of course, your question or provide you more resources on those things. And please remember to take up everything, because this room I think will be used for another meeting, okay? So I will see you in the lunch, and then Mike will tell us what to do. Thank you. See you later.